This video will be on chemical bonds, just the basics of covalent, ionic, dipole, hydrogen bonding, van der Waal interactions. As an overview, we have this outline. You can essentially say there are two types of chemical bonds. You have covalent and you have non-covalent. Now the different types of covalent are polar and non-polar, while the non-covalent is everything else, including ionic interactions, which are also known as coulombic interactions. You don't hear that very often though. We have dipole interactions. We have hydrogen bonding, which is a specific type of dipole interaction. And we have van der Waal interactions. Start with covalent. Basically, these are strong bonds. These are molecules that are very stuck together because they share electrons. So technically, we would say that the molecules share electrons because they have electronegativities that are close together. And by close together, we mean less than 2 units apart on the Pauling scale. Now what that means, first we'll start by defining electronegativity. This is basically the pull on electrons, kind of like you have in this cartoon here, where the hydrogens are pulling on their electrons. They each want to possess them, but the electronegativity is how strong they are, how hard they can pull. For example, you can have some charts that'll show you this. So on the Pauling scale, we could say that carbon has a 2.5 electronegativity. And if you have two molecules that are less than 2 apart, so for example a carbon and another carbon, which will both have the electronegativity of 2.5, there's no difference between them. No difference is definitely less than 2, therefore carbon and a carbon would make a covalent bond. So to sum up sort of all of what I just said, this is the sharing of electrons. Now for the types of covalent, you have polar, where there is very little difference in electronegativity. So one might have a slightly bigger electronegativity than the other, but not by much. In nonpolar, you have very, very little difference, or no difference at all. Like I said before, carbon and carbon, they have no difference at all. That would definitely be nonpolar. But for like oxygen and hydrogen, we would call that polar because oxygen is a little bit more electronegative than hydrogen. And how do we determine if it's more electronegative? You just look at the chart. You can see here, 2.5. The higher the number, the more electronegative it is. And overall, we say that the molecules are more polar when there's a bigger difference. So the more difference there is between them, between the two molecules that are covalently bonded, the more polar we say this is. That is until, or as long as it's less than 2 apart. We see covalent bonding frequently in organic molecules, for example, saccharides or sugars. Like if you think of the disaccharides where there's, say, a glucose and a galactose bound together. Those are bound by covalent interactions. Now, we did covalent, polar, nonpolar. Now I'm going to do everything else, the non-covalent interactions. First type I'm going to cover is ionic. This is sort of the opposite of covalent, you could say. Remember before covalent, it was less than 2 on the Pauling scale? Well, ionic have more than 2 on the Pauling scale. So say a molecule has an electronegativity of 4, and another molecule has an electronegativity of 1. That's 3 units difference between them. That is definitely more than 2, and it will cause them to have an ionic, an ionic bonding. So what happens is this huge difference. So remember, electronegativity is the strength. So you have a big difference in strength, which allows one atom to steal the electrons entirely. So going back to our little cartoon here, remember, they're pulling, pulling, pulling. Now, if one of these guys was way stronger than the other, they're going to end up stealing both electrons instead of sharing them, which is what happens in the case of table salt, or sodium chloride. We have our sodium here and our chlorine here. The little yellow dot is an electron. But chlorine, it originally belongs to sodium. But chlorine is way more electronegative, so it's way stronger at pulling on electrons. So instead of just pulling and they end up sharing, it steals it entirely, and you end up with chlorine having more electrons than it should, or it has -1 charge, as you can sort of see there. And now sodium has a +1 charge, because it lost the electron entirely. However, they're still bound together because the positive charge and the negative charge attract. So these are each called ions, since they have a different number of electrons now. So you can see ionic bonding between them, since the sodium ion and the chlorine ion are bonding because of the difference in charge, since the negative and the positive charges attract. The next type of non-covalent interaction is dipole interactions. Now these happen because of polar covalent molecules, but are not the same thing as polar covalent molecules. We could technically say that it's because of the unequal sharing of electrons. One side ends up more negative, one side ends up more positive. So remember before when we talked about covalent and non-polar, with polar. There's not much difference, but there is a little bit of difference in electronegativity. For example, in water, these little boomerang-shaped molecules are water, supposed to be water anyway. Now the red spots are oxygen, and the white spots are hydrogen. If you recall, oxygen is more electronegative than hydrogen, so even though they're still sharing and they're still covalent between these two, you end up with a slightly more negative charge on the oxygen, since it's pulling the electrons a little closer to itself than the hydrogen is. So the dipole interactions come between this molecule, which is covalently bonded, and its partial charges. Those little squiggly things are delta, and they represent partial charges. So this partial negative charge wants to be near something with a positive charge. For example, the magnesium here. So between this positively charged magnesium and this partially negatively charged water, this bond right here is called a dipole interaction. It won't stick together very well, but it definitely wants to stick to some extent, and it can make a huge difference in some cases, especially if you have a lot of this type of reaction. And just remember that this right here between the oxygen and the hydrogen is a covalent bond, but between the oxygen and this magnesium, that is the dipole interaction. So remember, dipole interactions will be between two different molecules. This is all one molecule, this is one atom. So you'll have between those two. Versus covalent, it'll all be between the same molecule. Now, there's a special type of dipole interaction called hydrogen bonding. Now, it's called hydrogen bonding because, as you can probably guess, it involves hydrogen. So this is sort of like what we saw before in our example of water. You can see the red is oxygen, and it pulls pretty hard. And the white spots are hydrogen. They don't pull quite as hard. So you end up with more negative charge on the oxygen, represented by the little delta minuses, and you end up with slightly more positive on the hydrogen, where you see the little delta pluses. Individually, these interactions aren't too strong. Altogether, they can be very strong. But what they're actually doing is the slightly positive on the hydrogen wants to be near the slightly negative on the oxygen. So the water molecules will arrange themselves to face this kind of direction, where each one wants to face the opposite charge. Two oxygens, for example, won't want to face each other because they're both slightly negative. An example of when this occurs is DNA. If you have two different strands of DNA, as we know, DNA is a double helix, and the two strands in the helix are held together by hydrogen bonds. So we have a whole bunch of hydrogen bonds all lined up in a row, which is actually very strong. Our last type of non-covalent bonding is van der Waal interactions. Now these are sort of vague interactions. They're very weak. They're weak interactions between all atoms, regardless of polarity. They're sort of like dipole interactions. Only dipole interactions only occur when you've got a polar molecule. Van der Waal can happen with a non-polar. So even though, theoretically, with a purely non-polar molecule like carbon-carbon stuck together, even though they are sharing the electrons equally, because they've got the same amount of electronegativity or pull, you still have what you would call an attractive or dispersion and a repulsive or steric component. What that means is that the electrons do exist and they do have a negative charge. So, like as our little classic atom picture here, you can see the electrons whizzing around, and at one point this electron's going to be here, but at a brief moment later it's going to be down here. They do move. So when it is on this side, you will have a slightly more negative charge on this side than that side. So if you have a slightly more negative charge on this side, it's going to push just a little bit on any molecule it comes near that has a slightly negative charge near it. So just from moment to moment, as the electrons happen to move around and happen to come across other molecules that do the same thing, it just gives a little bit of a push or a little bit of a pull, depending on which side of the molecule the electrons happen to be on at that exact moment. So you get a slight push away if you get two negatives that just happen to come across each other, or a slight pull if you have the negative charge on this side of the molecule come near the positive on another side of a different molecule.